So this isn't going to be a public video, but I'll give a link if you want to share this with anyone who needs help with this kind of thing. So in the email, it said that you were looking for help with instantaneous rate of change. And that is this formula, the definition of derivative. And that is just a fancy way of saying slope. The instantaneous rate of change is just the slope at a certain point of a function. And this formula is actually a much more difficult looking version of something that you've seen 100 times before. So if you remember, to find the slope of a line given 2 points, you had y2 minus y1 divided by x2 minus x1. So given 2 points, if I had a line and I had this point, I had x2, y2 up here, and I had x1, y1, you could find the slope of this line using this formula. But that only works because this whole line all has the same slope. So if you are trying to find the slope at a certain point of a function that looks like this, how are you going to do it? Because if you wanted the slope at this point, you said, what is the slope at this point in the function? Well, that's a line that kind of looks like this. That would be the slope. It'd be a line that would just touch the function. And so you can't use this formula because any other reference point you pick would give you a different line. So if I picked for my x2, y2, if I picked this point, then I use this formula, it would give me the slope of a line that goes through those two. And then if I pick this point, it would give me the slope of a line that goes through those two. And none of these are the slope of this function at this point. So that's what this formula does. It takes this formula that can only be used with a straight line, and then it allows you to do this same idea, but in a function that curves and curves. All right, so let's say we had, I'm going to draw it big here because it's kind of hard to see, but say we had this function and we needed the slope right here. So we're looking for the slope of a line that just touches the function. So you could say, we can't pick this point as our second reference, our x2, y2. We can't pick this point. But as we get closer and closer to that point that we're trying to find the slope of, say I picked a point right in front of it. All of a sudden, if I use this formula, I would find the slope of a line that looked a little bit like this. And as I got closer, it would look a little bit more accurate. And as I got, in fact, an infinity amount of close, then it would just get an infinity amount more accurate. And so if I picked, a point right on top of it, then it would, very, very, very close to it. It would, in fact, be a great approximation to the actual slope of that spot. And that is what this formula does. Now I'm going to start labeling these variables so you can see how this formula works on a graph and get like an intuition as to what is going on here and why it's so similar to this. So if I had this point and I needed a slope, we don't know. I'm not gonna give a number here. I'm not gonna say where we are. I'll just say that we're at some number, which I'll call x. Okay? And I'm trying to find. So this point is actually x, y. So we'll call that f of x, right? Because f of x is y. Now we'll pick a point, and we're gonna get closer and closer and closer. But for now, don't worry about that. We'll just pick another point. It doesn't matter where we pick the point. So that's going to be our x2, y2, like our second point that gets closer and closer. So we don't know where this is either. That could have been anywhere. We don't even need to put numbers on these things. We're just going to call that, we're going to say that the distance between this point and this point on the x-axis, so between here and here, we're going to call that distance h. Again, we don't need to assign a number to that. which is kind of a hard concept to grasp at first, that these things are generic. You don't need to assign values to them, and that's the beauty of the equation. So we have some kind of point this far down the x-axis. Then we have another point this far down the x-axis. And all we know is that the distance between them we're going to call h. Which means that because we have no numbers here, this point right here, how far is it down the x-axis? We don't know, except it is x plus h down the x-axis. You know, we went x amount, and then we went h more units. So this point, its x value is x plus h. So this point right here is actually at x plus h, f of x plus h, right? Simple. We put a number in for x, and then we got a number out for the y value. So we put x plus h in, got a number out for the y value. And then we say, okay, but that slope doesn't work. So let's move it closer, right? Sure. Let's say that h is a little bit closer. And then let's just keep moving h closer until all of a sudden we have a point. We say that h is so small, this distance is so small, it's right here. Now all of a sudden you have a point right here called x plus h, f of x plus h. Oops. And that is just about the slope at this point, which is the point we're trying to find the slope at. But then if we move even closer, we can keep making this h so small that it is effectively 0. So what you have here is, let's look at how it's worded on there, because how it's worded is a lot more confusing than, so again, we'll draw it further away just to give some space on the board here. So we have the distance h, and we have some kind of, we've gone x plus h down the board, and here we have x plus h, f of x plus h. All right, now we're just using this formula. Okay, this is y2, which is f of x plus h, minus y1, which is f of x. And then we want, instead of finding the distance between x's, that distance between x is going to just close and close and close. Sorry. It's just going to close and close and close because h is going to essentially be 0. And so we're just going to, instead of writing x plus h minus x, like you'd expect up here, like x2 minus x1, instead of writing x plus h minus x, we're just going to say what happens when x plus h minus x is essentially 0. And that is what you're doing here. You're finding the distance between the y values divided by the distance between the x values, which is going to be about 0. And that is something that you do have to be very mindful of in calculus, because you're not asking the question, what is going on when h equals 0? You're asking the question, what is going on when this distance is so small that it's effectively 0? All right, now we'll do an example of using the definition of derivative to find the derivative of a function. So given a function f of x, we'll call it x squared. That graph looks like this. It's a very common graph called a parabola. Now, if we want to find the slope at any one of these points, or if we want to find the instantaneous rate of change at any one of these points, so that slope, that slope, that slope, then we'll use the formula. So the formula is the limit as h approaches 0 of f of x plus h minus f of x divided by h. So f of x plus h is the same as f of x, but you just replace all the x's with x plus h. So instead of x squared in the numerator, we have the limit as h approaches 0 of x plus h squared. So we have x plus h squared minus f of x, so that's just x squared, divided by h. So if we FOIL this out to the side, just x plus h squared, we're just going to take that and FOIL it. You have x plus h times x plus h, and that will give us x squared plus 2xh plus h squared. And we can just put that right back into our formula. So we have the limit as h approaches 0 of this whole thing minus x squared. So x squared plus 2xh plus h squared minus x squared divided by h. So the x squareds subtract right off of each other. So we're left with the limit as h approaches 0 of 2xh plus h squared divided by h. So I can divide an h out of everything here. So I have the limit as h approaches 0. Dividing out an h, I have 2x plus h. Because I divided out one of these h's, I still have the other one. So we can find the limit as h approaches 0 of 2x plus h, and that will be the derivative. And if you've done limits, you know that this h, as it becomes 0, the limit ends up just being 2x. So f prime of x, which is the derivative of f of x, equals 2x. All right, so really quickly, let's compare the graphs. So if f of x equals x squared, we have a graph that looks like this. And its derivative, f prime of x, equals 2x, which you should kind of recognize as just a line with a slope of 2. Looks a lot like this. It's just a line with a slope of 2 through the origin. So let's think about it. If we want to find the instantaneous rate of change at a certain value for x of our function, or the slope at a certain value of x of our function, say I want to find the slope of -3 here of our function. So this is -3, x equals -3. Well, we know it's going to be a very negative number. It's going to be a larger negative number because we have a large negative slope right here. And sure enough, if we plug in -3 into the derivative, it will tell us that the slope is -6, because 2 times -3 is -6. So at x equals -3, our derivative is -6. So at, we'll call it -2. If we want to find the slope right here of f of -2, we can just plug -2 into our derivative, and that will be -4. And so here we have -2, and we can see that the output was -4. And what about 0? At 0, we see that the slope is just 0. And sure enough, if we plug 0 into our derivative, then we get 2 times 0, and that's 0. So at x equals 0, y is also 0. And so the way that these graphs are linked is that at any given point on this graph, on the derivative graph, any given value for y is just the slope of your original function. So it's pretty cool.